I'll be introducing our professor, Dr. Andrew West, who is a lecturer in our chemistry department, and I'll turn it over to you.
Great, thanks, Emma. Well, welcome everyone. I do want to encourage everyone throughout this, like I can talk easily the whole time, and I probably will talk a lot, but I want you guys to ask lots of questions. So as you have questions, um, write them in the Q&A. I'll do my best to make sure I can see them and all that as you're doing it. But I'm excited to talk to you a little bit before we start. I do actually want to give a quick poll, and just to kind of get you warmed up, get you thinking about what we're going to talk about. If you saw the title of the talk, which I haven't put up yet, is "We are all made of stardust." And I want to talk tonight just about like where the elements come from. So before we start, I want to do a poll, which I think you guys should have access to. Let's see if I can launch it. There's a poll right now. Boom. So why don't you guys take a quick poll of where are at least most of the elements made? And we'll just see what your thoughts are. I think you can answer multiple of these things. Just give that a minute. We'll do a couple of these tonight. Nice. All right. Well, if you're going to lock in your answer, do so in the next minute. Again, this isn't like right or wrong. We're not recording who did what. It's just to kind of get you warmed up. Here, let me share the results with you. Hopefully you guys can see that. So you can see it's like spread a little bit. Like about half of you said the Big Bang's one of the places. Some of you, about a third, said dying stars or exploding stars, and then about 14% said normal stars. So awesome. That's good. Well, by the end, you will know what the answers are. I'm going to leave it as a mystery. All right, so now I'm going to share my screen and we'll start the class. Okay, so let me find this. Boom. Look at that. Okay. And I don't know if, can you guys see my Q&A when I do that? Should I close that? Can you see it, Emma?
I was able to close out of it, so they can just X out.
Okay, perfect. Great. I'm going to leave it open in case you have a question you can write in. All right. So again, Emma said I'm Dr. Andrew West. I'm a lecturer in the chemistry department. I'm actually an astronomer, so it's a funny thing. But I also teach in the Tuppet program, which is Tufts Prison Initiative. So Emma said that you can click out of it if you want to click out the question and answer. Um, um, well, this is the way I start most of my classes at Tufts, with a set of questions. And these are all the questions that by the end of our short time tonight, you should be able to answer. Probably with like a short sentence or two, maybe even a little longer for each one. So let us begin. The two classes that I teach almost all the time at Tufts, in fact, every semester I teach a class called Big Bang to Humankind, which is a class that literally covers from the Big Bang beginning of the universe. It's like the beginning of like planet formation, star formation, Earth formation, and then we talk about chemistry and biology, and we end with anthropology. So it's like a little bit of science for everything. And I know some of you might be interested in science, and we can talk about that in the question and answer. Some of you might not be interested in science, but we'll still end up taking some science at Tufts as part of the distribution, uh, liberal arts experience. I also teach a couple classes, like I said, as part of the Tufts Prison Initiative, one called Alien Worlds, which is all about the new exoplanets or planets around other stars we've been finding, as well as the one called Concepts of the Cosmos. So here's like the roadmap. I want to get to you today to explain where this thing comes from. And many of you have probably taken high school chemistry, if not all, but maybe not all. And I hope that some of you learned where some of these elements came from, but I want to I want to like go into more detail. What I'm not going to go into is actually the first four elements. You can see the ones highlighted in red: hydrogen, helium, lithium, and beryllium. Those were all created in the Big Bang. Actually, in the very first 3 minutes that the universe was around. The universe has been around for 13.8 billion with a B years. And all of those elements, like almost all of the hydrogen and almost all of the helium in the universe, was formed in that first 3 minutes. So I'm not going to talk about that. I'm going to talk about things that happen much later in the universe. And so that's pretty exciting. If you've ever had like a helium balloon or something, or used helium in any way, like almost all of that helium in that balloon was formed in the very first 3 minutes of the universe. So that's kind of exciting, but a topic of a whole other lecture. I want to talk about stars. That's actually where my research area is. I study the very lowest mass stars. And the process of star formation is just amazing. This is a model made by my friend and colleague Matthew Bate, who's a professor at University of Exeter in England. And what he's done is taken a giant cloud of gas and put it into a giant computer simulation where he turns on gravity and some physics about the gas, and he lets it kind of play forward just using pretty simple physics. This simulation is color coded by temperature. So the kind of darker, redder colors are cooler, and the yellow or whiter is hotter. And what happens is when the gas reaches about 10 million Kelvin, 10 million degrees, it turns into a star. And you can see he's coded those in as little stars. And this is the process by which we think almost all stars form, that they form from big clouds of gas and in clusters of gas. Stars don't form as individuals. They form in big clusters. We think even the sun formed in a cluster of stars. And that over time, those stars were dissipated out. You can actually see in this simulation, stars begin moving out very quickly after they're formed. And that happened in the case of the sun and its cluster. And in fact, there are very few clusters that stay intact for long periods of time. We can see either really young clusters that are first forming when we do observations, or older ones that are much denser, made up of literally hundreds of thousands of stars. But the idea is this is kind of the beginning of star formation. We can see that happening in many places. This is a constellation that may be familiar to many of you who live in the northern hemisphere, although I guess you can see it in many places in the southern hemisphere. It's just turned upside down. I used to go observe in Chile all the time, and you could see it just was upside down in the sky from what it looks like, at least here. This is the constellation Orion, the star Betelgeuse, which is a red star, which we'll talk about maybe in a little bit. There's a blue star Rigel here. And then if you look really carefully in this belt or sword of Orion, the middle star is actually kind of fuzzy. That's actually called the Orion Nebula. And it's a place, here's a zoomed in, very long exposure telescope image. It's beautiful. This is a place where new stars are forming. It's actually pretty far away, but it's one of the closest places in our galaxy where we can observe new stars forming. And, again, I could spend a whole class just talking about the process by which stars form. But I want to talk about what happens once they do form. When stars form in a cluster environment or in the Orion Nebula, all stars aren't formed of the same size. In fact, this is uh, a image showing the collection of all the stars within what astronomers call 10 parsecs, which is about 30 light years. Those distances are really big. And again, I don't have the time to really introduce those giant distances. Just think that like a light year, which sounds like a unit of time, is really a unit of distance. It's the distance that light travels in 1 year. All right. And that's a really, really, really far distance. Just light minutes is like what we deal with in our solar system. I mean, some of you may know this, but the sun, it takes 8 minutes for the sun to get from the sun to the earth. So like if the sun went out, you wouldn't know for 8 minutes. And that also tells you a really other cool thing about astronomy, that everything we observe is in the past, right? So if you're looking at the sun, which you shouldn't look directly at, but if you're looking at it, you're looking at it not as it is right now, but as it was 8 minutes ago. When we look up at the night sky at all these stars, we're looking at these stars not as they are right now, but as they were hundreds, or in many cases, thousands of years ago. So it's really cool. It's like the ultimate in history project. So this is a census of all the stars. And the sun is, you can see they're labeled by either colors or letters if you look along the bottom. The sun is actually one of the yellow ones. And so you can see there are other stars like the sun. There are a few that are, and they're coded by the sizes of them represent how bigger they are. There's some stars that are bigger than the sun, and there's a lot of stars that are smaller than the sun. In fact, most of the stars in the galaxy are these tiny red ones that you can see. And those are actually the stars that I study, but they are by far the most numerous. 75 to 80% of all the stars in the galaxy are these little tiny ones that are cooler and dimmer. Another way of thinking about all the stars that we see is if you plot the brightness of the stars. We call it the luminosity, but that's just a fancy word for like how much energy they're putting out, or how bright they are, like intrinsically. Like, like if you're talking about a light bulb, you might call it 100-watt light bulb or a 50-watt light bulb. All you're talking about is how bright that bulb is. That's all we're showing in this plot. So the vertical axis is how bright the star is, and the horizontal axis is what its color or temperature is. And I actually said those two together. You may or may not know that everything with temperature gives off light, right? That things that are really, really hot are actually really blue, and things that are red are really cool. So whoever invented the faucets, the colors on the faucets, was certainly not a physicist or a chemist. They were not really that smart, because blue light is higher energy and is what really hot things give off, and red light is what still hot but cooler things give off. And you all know that if you've held up a match or a lighter, you know that you can see like kind of a red part, a kind of white part, and a blue part. And the blue part is the hottest part. So stars are the same way, and we see that stars are actually aligned in these very nice patterns if we just plot how bright they are versus their color. They don't fill all of the space. There's this part in the middle that we call the main sequence, and that's where stars that are undergoing their normal life live. Like that's where the sun is right now. It's actually right, I don't see my cursor, but it is at a luminosity of 1 if you can look to the left. It's a G type star if you can see the G at the top. And stars on that main sequence are just kind of living their normal life. And you can see that they come in lots of different varieties, like I showed you before. You have stars that are hotter and brighter and bluer on the left-hand side of the diagram. And on the right-hand diagram, you have stars that are cooler and dimmer and smaller. And you also see, I love this diagram because it shows that, again, those small stars are most numerous, and the stars on the left side, the blue side of the main sequence, are the most are not very numerous. In fact, there are none of those in nearby the sun, and that's actually a good thing, it turns out, for us, as we'll see in a second. I do want to take a step back and just talk about like briefly how the sun works. This is actually a picture of the sun taken a couple days ago by the Solar Dynamics Observatory, which is a NASA-run observatory that's constantly taking images of the sun in lots of different wavelengths. This is the one in the type of light that you and I see. I can't actually read. Oh, how do I move that? I see there are questions, but I can't read them because I'm in the way. I don't have my cursor. Let's see. Oh, look at that. Oh, here we go. I thought that the blue light in lighter fires was because of the fuel burning. Oh, there is actually a chemical component to some of the blue, but a better example would be like light bulbs. Like, so you can get light bulbs that are red, or you can get light bulbs that are um, uh, light bulbs that are blue, or light bulbs that are white, and like incandescent old school light bulbs. And those actually like are reflective of how hot they are. And in fact, if you got a blue light bulb, it's actually hotter than the sun. Um, and it's actually, to answer the question, I thought Sophia asked, like, I thought it was just the type of gas that burns blue. Well, not exactly, right? Because like it's the same gas that's burning in your lighter, right? If you light your lighter, it's the same gas, but part of it's yellow, part of it's blue, and part of it's um red, right? And so the blue part is actually hotter than the white part. You're right that the color is not solely based on temperature, but certainly the bluer colors are indeed hotter. That's an awesome question. That's great. All right, I'm gonna move on. There we go. Okay, so this is how stars work. Again, in a class, I would never have students like, well, in an introductory class for non-majors, never have them memorize like all of this, what's happening. But what I want you to see is that the sun and all stars are not on fire. They are not, burning or any like terms like that. What they're actually doing is smashing atoms together. That the sun and all stars at their central parts are so hot that they are literally smashing particles together and they're producing other elements and light. And that's fundamental to like how stars ultimately produce not only light, but other elements. Now, all stars living their normal life, like the sun right now, are smashing what's shown in this diagram, are smashing protons, which is just the nucleus of a hydrogen atom. Proton, the middle of atoms is either has protons or neutrons, and the most simple atom is hydrogen, which in its most common state is just protons. They're smashing protons together, and they're smashing so many of them together that they're producing light, and the end product of that is hydrogen. You can see from this diagram, there's all sorts of other funny things that come out, like some other kinds of helium and these funny particles like neutrinos. And again, happy to chat more about some of those details in the end. But I want you to walk away knowing that the way the sun and other stars work when they're living their normal lives is just smashing essentially hydrogen together to make helium and light. That's like all that any star is doing. So the sun right now is just smashing hydrogen together to make helium. In fact, any normal star, that's what they're doing. And the cool thing is, remember I told you at the beginning that helium's really mostly made in the Big Bang? Well, all stars are making helium. And there are hundreds of billions of stars in our galaxy and hundreds of billions of stars or galaxies in our observable universe. And yet they're not making a dent in the amount of helium that was made in the early universe in that first 3 minutes, which is just mind blowing to me. That like all these stars are constantly making helium, and yet it doesn't make any difference. Like almost all the helium was still made in that first 3 minutes of the entire universe, which I think is cool. The last thing I want to show you in this quick like view of stellar evolution, if we're again just concentrating on that main sequence, that kind of middle thing in the middle of the diagram, it's labeled main sequence, is that the bigger blue, brighter, bluer stars live different amounts of time um, than the smaller, redder stars. But I'm going to pause for a question. Is helium renewable in space, or does it just get consumed? Um, it is more, some of it is made in stars, and then those stars will actually spit it back out into the galaxy, and we'll talk about that in just a couple of minutes. But like in individual places like the Earth, helium is not renewable. So we have a finite amount of helium. Most of it's trapped actually in rocks under the ground. And it's actually, we have a bit of a shortage now. And you can't actually produce, we have no way of producing more helium or gathering it from space. So once we're out of it, we're out of it. Whether that's good or bad, I don't know. But that is the case with helium. With other elements, you can actually do some chemical reactions and free them, but helium is not like that, partly because it's a noble gas. Back to stellar lifetimes. The way I teach this in my class, I tell a story about when I was in high school living in Northern California, like I know some of you guys do, because I saw where you're from. My dad went through like kind of a midlife thing, and he bought himself a car, this car actually. It was a V8 T-top Camaro, And it went really, really fast. And I know this because I was a teenage driver. I'm sure all of you guys are very responsible. But this is like a really big star, right? It had a ginormous gas tank. It went really, really fast, but it got really terrible gas mileage, like super terrible gas mileage. And the big stars are just like that. They're less efficient. They have really short lifetimes. And in when we're talking astronomy, the time scales are big, but these are short lifetimes. Like the biggest stars last less than 1 million years, like hundreds of thousands of years, which, on geologic and astronomical timescales is like instantly. They form and then they die. On the flip side, this is me, a much younger version of me. This is what I drove in Northern California, a 1969 Volkswagen Beetle, which has a very small gas tank, if you've ever had the luxury of driving one. It does not go very fast. I tried like having it, drive down a hill like shaking, and it just did not go very fast. But it got amazing gas mileage. It could go like all over Northern California without me having to fill up. So these are more efficient, longer lifetimes. And in fact, the smallest stars have lifetimes we think like measuring well over 1 trillion years with a T. And you might say, like, well, that's longer than the universe. How do you know that is? I mean, the cool thing is, like, it's true. Not a single one of those stars has ever died because their lifetimes are so long. And we know it the same way your car can program. Most of you probably have modern cars, your parents have modern cars where like it tells you how many miles till empty. Well, we can do the same thing with the star. We can see how much gas it's using. We can see how much it has in its reservoir. We can make those estimates very actually with pretty high precision, and then we can calculate how long it'll take to die, just the way your car does. So eventually, stars die. They run out of gas, just like a car. It's a good analogy. And eventually they will run out of gas. And when they do so, gravity, that the whole time a star is alive, is trying to like make the star get smaller, but it doesn't because all of the energy from the nuclear reactions in the center is actually holding the star up. But what happens when the star runs out of gas is the gravity wins and it starts to compress the star and make it even hotter. That makes the core really hot, and the star actually expands because it gets so hot now from that second collapse that it actually gets bigger, and it gets not only big as it was originally, but gets even bigger. In the sun's case, it will get ginormous, and in that getting bigger, the star will have much larger surface area, and the outer part will cool. The inner part will actually be really hot, hotter than the original star was at the center, but the outer part will be much cooler and it will become a red giant, which we did see in the upper right-hand corner of that HR diagram. This is a cartoon of showing you kind of what the sun will become, the size of the sun when it becomes a red giant. You can see here the sun, you can see the tiny little dot that is the Earth. This is to scale, and then to scale is the red giant there, sun, which will be much, much bigger. The our estimates based on the sun's mass and what we've observed from other stars of similar mass and type as the sun is that the sun, which still has another, 5-6 billion years left. Sun's been around for about 4.6 billion years and has a lifetime of about 10 billion years. So we're almost about halfway through. So it's not happening anytime soon. But we think that the radius of the sun will be about 1 astronomical unit, which is about the same exact distance that the Earth is from the sun. So this is probably the end of the Earth. Well, it's certainly the end of the Earth, because even if it gets just like 95% of the distance to the Earth's still going to get incinerated. So if you want to know like when the Earth finally is end, it's in about 5 or 6 billion years. No more Earth. I know that's kind of depressing, but the cool thing about red giants is that I told you the inner part gets so much hotter that no longer is it just smashing hydrogen together to make helium. Now you can take that helium and smash it together and make things like carbon. Oh my gosh. So this is how the red giants are making light. they're smashing things like helium together. This is the one of the reactions that happens. It's called the triple alpha process because chemists often and some physicists often refer to helium nuclei as alpha particles. You may have heard that term. They're just referring to like the nuclei of helium atoms. And when you smash three of those together, if you can get it really, really hot, we're talking now like tens of millions of degrees. Now you can smash those together and make carbon. So all of that carbon that's in your genetic code that, has your DNA, that amino acids, the lipids, the long lipid chains that make up your cell walls, all of those things are made mostly of carbon. I mean, that's the base of our life. That all was formed in a red giant star. Hopefully you know that. If you didn't, man, that's awesome. So same thing happens over and over again. Eventually, you run out of helium to fuse. And so what happens? The star collapses again. Guess what? It gets hotter. And when it gets hotter, it can now fuse something else. So the inside of some red giants, at the very core, you can see in this image, there's the big red giant on the right. And if you zoom into the core, you can actually see that there's like all these rings of fusion happen. Like you have first you start fusing helium to make carbon, then you actually add another helium to carbon and you start making oxygen. You make neon, you make magnesium, you can read it all the way down. This happens all the way down to iron, at least in massive stars. Um, with stars that are about the mass of the sun will certainly make carbon. It might make a little bit of oxygen, but it's probably going to stop there just because it doesn't have enough mass to go through this process. But for the most massive stars, they're going to make all the way up through iron. And the reason you can't go beyond iron is actually to make the elements beyond iron, you have to actually inject more energy into the situation. You don't actually get energy out. And so these processes for the stars to function need to get energy out to actually hold up the structure of the star, or else the whole thing collapses. So as soon as it gets to iron, the process is done. So it makes iron, and then the process is done. This is vital to like you and me sitting here and to the planet we live on and all of that, because it is in this process in red giant stars where you get carbon, where you get nitrogen, where you get oxygen, where you get iron, where you get silicon, that are vital to us living here today, right? I want everyone to take a pause and take a deep breath in. So you just breathed in mostly nitrogen and a little bit of oxygen. All of those elements were formed in the core of a red giant, not our sun, because our sun's only making helium, remember? In some giant distant in the past that formed that material, and then it was redistributed back into the galaxy. And then another star was formed from it, and it formed more of that material, and then it redistributed it back into the galaxy. We think that our star is a fourth, fifth, maybe even sixth generation star in this part of the galaxy. We are formed from recycled material, from recycled stardust. And every time you take that breath in, you are breathing in material that the only way we know how to make is inside the nuclear furnace of a dying star, which is just amazing. Hope you think of that. I mean, think of the planet we live on, which you may or may not know, the biggest element in the earth is oxygen, not in the air, but like if you pick up a rock, it's mostly made of oxygen, right? It's got some silicon and maybe iron or magnesium or something like that, but most of it is oxygen. Again, you can't build planets without things like iron and silicon and oxygen. So, this stage is so vital. So when we look at this periodic table, again, first 3 minutes give us those first elements. All the elements labeled in green up through iron, again, including all of the ones that are vital to our biology and biochemistry, are from the dying remnants of mostly massive stars. Now, I've got a few minutes to go through like how we get the rest, but I just want to finish what happens to the sun in case you didn't know. After the red giant phase, the sun puffs out its outer layer, the outer layers of the red giant. This is not an explosive event. It's not a powerful event, and it actually is not very much mass is lost off the sun. And you get these beautiful things that I hope you've seen. You can just Google planetary nebula. That's what the sun will be kind of come in its next stage. They have nothing to do with planets. It's a terrible name, but it's a historical name because astronomers thought they looked like the colors of planets. But it has nothing to do with planets. The sun will become one of these. The specific shapes actually depend on things like the magnetic fields of the star, which is actually, I think, a really cool thing. Um, at the center of each of these, this is one you can actually see with a really small telescope or binoculars. It's called the Ring Nebula. And at the center, if you look really close at the center, you see this little white dot. That is what the remnant, that's the end of the sun. And that's actually an object called a white dwarf. And a white dwarf is an object that's about the mass of the sun. Again, not much mass is blown off in the planetary nebula, but about the size of the Earth. So it's this really dense object. And basically, that's just going to hang out in space forever. It's actually kind of a waste of all of the carbon and oxygen the sun will make. It's just going to be stuck in that white dwarf forever. But the exciting thing happens, and the important part about this story, it would be really boring and nothing would happen. And actually, there would be like no us if all stars just ended their lives as white dwarfs because all that material. What's a white dwarf made of? It's made of actually mostly carbon and oxygen from the core, and then some hydrogen and helium because that's what like everything in space is made of. But yeah, a lot of carbon and oxygen. Basically, all the carbon and oxygen that was made in that red giant phase is stuck in the white dwarf. And it's just actually compressed as tight as electrons will allow it to press. Like gravity's still pushing down because it's very massive, but the electrons are actually pushing back. Many of you learned in like chemistry class, you have like spin up and spin down electrons. If you didn't, don't worry about it. And that's actually called the Pauli exclusion principle. And there's a way of packing electrons. And white dwarfs are actually as tight as you can possibly pack electrons, which is kind of cool that nature does that. If stars are larger, or sorry, I say more massive, not larger, more massive than about 8 times as masses of the sun, they also become red giants. They make all those elements. In fact, they make up to iron, but they do something really important. They explode as supernova, as one of the most powerful explosions in all of nature. These explosions are amazing. They are um, super powerful. They are super giant. You know, they go many, many light years in distance, tens of light years. So they not only destroy everything in their wake, but they redistribute all of that material that was made inside that red giant. They distribute it back into the galaxy from which new stars can form once the material cools down and recollapses and all of that again. So it's a ridiculously important process. But there's one more thing that happens during a supernova. Remember, it's a major energetic event. So what did I say you need to do to form heavier elements over than iron? You got to add energy. Well, the supernova supplies that energy. And there's lots of different pathways to make other elements. I'm just going to show you one of them. If you have iron and in this explosion, there's all sorts of material. The elements go flying, all sorts of protons and neutrons and electrons and all sorts of subatomic particles, along with lots of light, get thrown off into the universe. Well, if you have an iron nucleus and it gets bombarded by neutrons, it turns out like those neutrons are so energetic and moving so fast, they can actually get absorbed by other nuclei of atoms. And the atom says, "Oh, wow, I'm much more massive now." But it turns out that like neutrons by themselves don't want to be neutrons anymore. They actually want to turn into protons. And that's a whole other story of like why we're here and a really cool thing. But if you have roughly an equal number of neutrons and protons, they stay pretty stable. But if you inject a bunch of them into this nucleus, there's way more neutrons than can be stable. And so it decays from those neutrons turn into protons and it becomes a new element, an element beyond iron. And so what I put right here is the pathway of turning, or one of the pathways of turning iron into gold. So if any of you are sitting there out there behind your computer watching this, wearing gold earrings or gold necklace or gold ring, you are wearing material that the only way we know how to make it is inside an exploding star. You are literally wearing the product of a supernova explosion. Same with silver. Most of the like metals that we would call metals were manufactured in the explosion of a dying massive star. Isn't that cool? So think about that next time you put on a piece of jewelry. And that is how we form most of these most of the other elements on the periodic table. The ones that are still in white, which I haven't talked about, these are ones that have only been identified in the lab or in an accelerator here on Earth. They're typically called like human-made. These likely are all also formed in a supernova event, but they have lifetimes that are much less than a second. They're like they dissipate very quickly. And so, when we're observing them out in space, we don't observe the supernova like immediately when it goes off. It's usually like hours or days after the event. And so by then, any of these other heavy elements that were formed would be gone. But they likely are also formed in stellar explosions. Just the only place we've observed them is in labs on Earth. What's left after the supernova is called a neutron star. And a neutron star, kind of analogous to the white dwarf, is an object where it's about again, the mass of the sun, but it's about the size of the city. So of a good sized city. And so you've packed all of that mass into this tiny, tiny, tiny package. So it's really dense. The surface gravity is crazy. Like if you could beam down to the surface of this thing, you would be flattened instantly, like down to like one, atom layer. Like you would just be squished perfectly flat. Um, the neutron star, again, analogous to the white dwarf, is as tight as neutrons can be packed. And that's why it's called a neutron star. These have been observed. There's a famous set of them called pulsars that actually rotate and they pulse a beam of radio light typically every time they rotate around. And so we actually see them out in space in that way. What's maybe really exciting for some of you, although doesn't have a lot to do with the elements, but for the most massive stars, which actually I guess are important still in manufacturing elements, in that they also, most of them go through red giant phase, which manufactures up through iron, and they explode as supernova. But if they are about 25 times more massive than the sun, the initial star, they end their life not as a neutron star, but as a black hole. And that's because the neutrons can't support that much mass. And so what ends up happening if the gravity is just too great and it becomes a black hole. So black holes you may have seen in like the media or movies or things like that. Black holes are real objects. They are objects that are singularities. They have no volume. They take up no space at all. They have no size, but they actually have mass. So they have infinite density. And the way it actually works is, I mean, again, this is the subject of probably a whole other lecture, but the way gravity really works is by bending space-time. So, like when the Earth's going around the sun, there's not like a magic force binding it to it that we call gravity. It's actually that the sun is actually bending space. And then, so the sun's just, the Earth thinks it's traveling in a straight line, but through a bent space. And this was one of Einstein's idea that's actually been totally confirmed in like during solar eclipses and actually looking at clusters of galaxies. We can actually see how space is actually being bent. And yes, so black holes, like at least the small black holes like we call them stellar mass black holes that we see all over our galaxy, are just dead stars, dead really massive stars. So every really massive star ends its life as a black hole. What else was I going to say about black holes? Oh, so the way gravity works is essentially a black hole is when gravity has gotten so great right at the black hole that it folds space in over on itself. And so that object still has mass, but you've folded space in on itself. And so there's no more actual volume or space. So that's black holes. I'll give you a few pieces of evidence of them, just so you know. This is actually a cartoon, but I'll show you the real image. It's true that often really massive stars come in pairs. And if your stars like the sun, it's about 50%, and the lowest mass star is almost never. But if they're really massive, almost all of them have a companion. And so if you have one turn into a black hole, sometimes it can suck material off the companion, which is what you see here. And before it goes directly in the black hole and is gone forever, it kind of spirals around the drain, just like when you let out the water of the bathtub. It goes around and around and around. Um, so, and when it does that, I'll get to your questions in a second. When it does that, that gas heats up really fast. And so it actually gives off X-rays. So this is actually an image, it's an old image of the very first black hole that was ever detected. And it's a X-ray disk. It's a disk that is so hot, it's literally millions of degrees. And so it's glowing in the X-ray. And then if you took an optical image of this or infrared or any other things, there's nothing there. And we can actually see how fast that disk is moving by using something called the Doppler effect. And it's moving crazy fast. We can measure the mass that must be at the center to be moving those gas particles around. And it's about something the mass of the sun. And yet we don't see any light. So this is actually like the first piece of evidence of the black hole. I'll get to some questions now. The black hole has infinite density. Was it also have infinite gravity? No, because gravity has nothing to do with like the size of something, right? It's just the mass. So now, obviously, if you stood on the black hole, but that's a silly question because there's no size, so you can't stand on it. But in terms of its pull, no, it's just like if it's one solar mass, it's the same as a star. I don't think we'll have time, but I was going to give you another poll that's like, what happens if the sun turned into a black hole? Well, nothing. It would get dark, right? But nothing gets sucked in. This is where like I feel like people in maybe it's the media or other things get this totally wrong. Like black holes don't have any more gravity than anything else. They have mass and so they pull. The thing that's different is you can get really close to a black hole. You can't get really close to a star because you get incinerated. Someone asked, so gravity isn't what keeps the Earth orbiting the sun. We're actually traveling in the straight line, but it's the sun's mass that's warping space. Well, yeah, but that's gravity. So I would say it is gravity. Like the way gravity actually works is by warping space. I mean, many of you in high school have learned like Newton's law for gravity, which is actually wrong. And hopefully your physics teacher or your science teacher told you it was wrong, but it actually is wrong. It's a really good approximation for how things work, but it's actually not right at all. The way gravity really works is by any massive object, including you and me, we actually warp space a little bit. So I wouldn't say it's not gravity. It is gravity, but it's not like magic Newton where there's just like GMM over R squared. It's actually just moving through warp space. Do you have any thoughts on sources of white holes or other side of black holes? Well, I have some like thoughts or maybe beliefs that if we have time at the end, I'm happy to talk about. But like we have no, like scientifically, we have no evidence for anything. Um, could you explain the significance of electrons spinning in tight compact space in the white dwarfs? I'm currently looking into quantum mechanics and molecular orbital theory in my organic chemistry class. Yeah, so this is more than this being a like quantum mechanical problem. It's what's called like, what do they call it in chemistry? In physics, we call it a statistical mechanics or physical chemistry. So it's a property of like the electrons. It's actually not, I mean, it's a quantum property in that you're occupying states, but it's actually so what we call like physical chemistry or statistical chemistry, that when you actually make things really tightly packed, they actually produce a force. Um, so, and of course, yes, but the sun can't become a black hole. No, the sun can't become a black hole. It's not massive enough. That's just a thought question. There actually was this is a image of a black hole. or at least of what is called the event horizon of a black hole, the point of more return, of no return. Um, and this is actually a supermassive black hole that's at the center of a galaxy. We think that most galaxies actually have black holes at the center. Ours does. This is one. They're formed probably in a different way, but I thought I would show this because I think it's such an amazing image. That black thing you see is this actual point of no return that even if you shine light into it, it actually can't get out. And that's just because the gravity is so great, which means space is so bent that even light will never get out. Sam asks, hole implies that there's another side. I don't agree. Like if you dig a hole, there's not another side. You just like have a pit that you've put stuff in. So a black hole doesn't actually have to have another side. It could literally just be a place to deposit mass in this other dimension of space. I mean, that's the thing that's really happening here, right? Is that, you know, if you think of like, if we have like a two-dimensional sheet and like we bend it, right? That's easy to think about. But in reality, what's happening is you have three-dimensional space. You're bending to a fourth dimension. So you're actually bending into time. And so it is actually true that in the presence of a very gravitationally strong object, you're right near a mass where the gravity is great, where space has been bent, time is different than when you're outside of that. So if you've seen the movie like Interstellar or something like that, they actually got that part right. They did some playing around with how much time, but it is actually true. If you're really close to a black hole, your time would be different than way outside of the black hole. Time is not the same everywhere in space. And one of the ways it can change is if you're really near a strong gravity, because space has literally been bent into time. So do we know where black holes lead to? No, I mean, they might lead to nothing. But I think that's an okay answer we should all be okay with. It could just be literally that you're taking that mass. I mean, they still have mass, but you're just bending space into time. That's a totally acceptable answer. In fact, I like that one the best rather than being, yeah, they could be a wormhole, but I think that's silly. That's like sci-fi, like, I mean, it's not a silly question for you to ask. It's a notion that's like fun to think about. But I think in science and nature, we often see that like the simplest things are actually the most like what the solution ends up being. Are we able to measure the mass of things like stars and black holes? Oh yeah, easily. And we do that by looking at their gravity. So we look at how they interact with either planets around them or black holes, things spinning around them. So we can actually measure the mass to actually ridiculously high accuracy and precision around stars and black holes by just using gravity. I mean, that's how we do it everywhere else. I know I've answered a lot of questions already, but I want to make sure there's a lot of time for more, so you guys can ask questions about what might talk or science or Tufts or classes you might take at Tufts. So I want to just end this part and then we can ask as many more questions as you want. And I'm happy to stay as long as Emma will let me, or she wants to stay. I want you to walk away from this. Let's all take one more breath. And you may have heard this before. You may have heard that you're made of stardust before, but I hope that like after today, which I know was like rushed in a quick version, but I hope you see that like when you take a breath in, when you think about the materials that you're encountering on a daily basis or that our planet is made of, that is all material that was made in the nuclear furnace of a dying star. And if you're wearing jewelry like gold or silver, that was made, or zinc, or you can look at any of these things in blue or red. That's all made in the explosive event of a dead star. Like, I find that just amazing. I mean, I've taught this a million times and think about it all the time, but I still find that amazing that like that ended up here to form our sun and our planets. And and again, it's the ultimate in recycling project. So I hope you leave tonight a little more excited about what you could learn at Tufts, but also leave tonight, no matter where you end up, really understanding that you really are made of stardust. So thank you for your attention. I'm happy to ask again any questions, answer any questions about either the material, other classes I teach, Tufts, whatever. and anything's fair game, so great. This may not be the most relevant, but I was wondering how you feel about potential fusion as an energy source. Oh, that's a great question. So, this fusion, similar to like how a star works, smashing protons together to make energy, is actually like something that's being researched right now by physicists and engineers to actually be a energy source. And the reason being, it's ridiculously efficient. It's way more efficient than any of the other energy we use. Um, I think that the research is amazing. I mean, I fully believe in like funding lots of interesting like research. I don't think it's a good thing if like that's all we're putting our energy towards like solving the climate crisis or things like that. Just because like we know some other ways to do that, like through solar or bettering solar or things like that. And I think we're a long way off like fusion actually being something useful for us. But I definitely think it's a cool thing that we should keep researching just because I think someday it will be useful. Diana, I'm sorry, I have to, oh, well, there we go. Now I can read it. Here, I'm going to stop my share. There you go. Now I can read all your questions easily. So Diana asks, in your classes at Tufts, do you come across students with double majors in different topics a lot? Oh yeah, definitely. I mean, I'm not sure I've seen philosophy and astronomy, but that would be an amazing one. But I would say like a large fraction of my students have double majors, sometimes in totally different things, like an art and a social science or a social science and a science sometimes. You know, so totally that. I mean, I'll tell you myself, I I was an astronomy and physics major, but I actually minored in religion. I just couldn't do like the triple major, but like I was very interested in that. So it's very similar to your philosophy and astronomy. Are all the Tufts professors and as fun and passionate about their topics? Uh, I don't know. I don't know. I've not actually attended that many classes. The Big Bang to Humankind class I teach, I run the class and I teach about half of the material, maybe a little over half. And then I have an anthropologist who teaches the anthropology part because I'm not qualified to do that. And then I bring in a chemist and biologist to bring in the other. And I can say the people we have teach that part of the class who I have seen are amazing and enthusiastic and love their topic. And so, yes. What's my favorite thing to teach about Tufts? Oh, that's an awesome question. Tufts is a really wonderful place to teach because it really is a community. And I know like maybe like the admissions material says that and you've heard that at other places, but like I've actually taught at a lot of institutions or been a grad student or student at a lot of institutions or did my research training. And Tufts is, a place where education is forefront. Like we really are committed to like teaching undergraduates and really thinking about how we teach undergraduates. And yet it also is a research university. So there are faculty doing like cutting edge research, which undergrads can be involved in. But it doesn't feel like a giant university that you can kind of get lost. It really does feel like a community. And one of the things I love is that I have now taught thousands of Tufts students, and I teach about 200 every semester. So just me walking around campus, I see students that I have had in class like every day. I basically cannot walk from one place to the other without seeing previous students. And I actually try to learn as many of their names as I can. I don't get all 200, I'll be honest, but I get actually a lot of them. Are engineers able to double major? It probably depends exactly what, and it probably depends like what you, oh, Emma's writing that, so I'll let her answer. She
Yeah,
did.
I'm happy to jump in here
Yeah,
on the admission side. Oh, I can turn my camera back on.
yeah.
Come back out from behind the scenes. So it is less popular for engineering students to double major, but it is possible. So if you're interested in that and you come into Tufts kind of having these ideas about how you want to combine these different areas through a double major, that is something that students can talk with their advisor about and make a plan. It's just not as common as within arts and sciences. It's significantly easier, but it is super popular for our engineers to have minors, both in the School of Engineering and the School of Arts and Sciences. So our engineers definitely do get to have the opportunity to explore different academic areas as well.
Yeah. And like I said, I have a lot of students who are like SFMA arts and science double major. So like they are cross college, but not engineering. But all right, I'm gonna see if I can get through more of these. Do you know if it has any connection with NASA or companies similar? Sure. Yeah, like in the physics and astronomy department, there's lots of people working with NASA, either getting NASA funding, which is one of the funding industries, or working with, one of the physics astronomy faculty, like works with a lot of the space telescopes, has been using Hubble and now the James Webb Space Telescope. So lots of things like that. Let's see, do I have any research ongoing? I do. So I mostly work with very large samples of data. So with like images of literally millions of stars. I also do something called spectroscopy, where I divide all the light out from the star to understand what stars are made of and how fast they're moving. And I actually am working right now with a sample of almost about 100,000 stars. And I'm trying to understand questions of how fast the galaxy is moving using these stars as tracers, and how old these stars are. That's like, I would say my main research question is trying to actually tell how old a star is, which is not always the easiest thing to figure out. We can tell how long they live pretty easily, but finding how old they actually are is a little bit hard. Do I find students more cooperative or competitive? Oh, that's hard for me to answer as a professor. I mean, they seem very cooperative. I do a lot of group work in my classes. I actually don't do a final exam either. I actually do a final creative project that most students actually choose to do in groups. And so I really encourage like cooperative learning. In fact, even in class, I do lots of polls. Like I tried to do some, or at least one with you. I try to do lots of polls where I'm trying to get students engaged in even a giant lecture class. And sometimes they turn to their neighbor to explain. So I don't know, I found them very collaborative, but I'm not a tough student, so it's a harder thing to answer. Looking to double major environmental engineering and sports analytics. That might be a question more for Emma, since I don't know.
Yeah, I'm happy to jump in here. So we don't have specifically like a sports analytics major or minor at Tufts, but you could definitely be taking classes in different sorts of areas to learn about sports, learn about analytics in different ways as well. So it would be really common for Tufts students, as Dr. West mentioned earlier, who are studying all sorts of different academic areas and combining them. So you could definitely be studying environmental engineering as well as like some analytics pieces, some sports pieces. So you could have some combinations there.
Yeah, implications of Polaris going supernova. Polaris is actually pretty far away. There are no stars in our close vicinity that are going to go supernova, which is good because any star going even like, you know, few tens of light years from us, even though like the blast wouldn't like probably get to us, the high energy light would get to us, and that would be potentially very damaging to us. But there aren't any big stars near us. So there aren't, I mean, there's no real implications if Polaris were to go supernova. I actually don't remember actually what type of star exactly Polaris is. To be honest. We wouldn't have a North Star anymore. But that changes anyway, right? Like when as the Earth does this thing called precession, it like wobbles like a top. If you spin a top, you notice it spins really fast, but there's like a slower spin. Like the top of it looks like it's slower spinning. That's actually called precession, and the Earth does that too. It does like it's like a just over 20,000 year cycle. It's why like none of you are the zodiac sign you think you are. I hate to break it to you. It's like 1 month off. So like my birthday's the end of February. People would say I'm a Pisces, but I'm really not. I'm an Aquarius. So maybe if you've learned something tonight, you've learned that you're not a Gemini, you're not a Sagittarius. Do I have any tips for astrophysics majors? Yeah, I mean, the biggest thing is get involved in research, no matter where you go. That's like easy to do at a place like Tufts. It's true lots of places. But ask lots of questions of your faculty. Like you're going to take physics classes that are hard, you know, ask lots of questions of your faculty. And the big thing that most people neglect, learn to write. Um, I think that lots of science majors kind of say, oh, that's a humanities skill. And the number one skill to be a professional scientist that you need has nothing to do with like math or science. It's writing. You have to be a good writer because you have to communicate your ideas when you're sharing your results. You have to communicate your ideas when you're asking for grant funding. And the people who succeed in this business, the only ones who succeed are the ones who are good writers. So that's probably the best. Can you see the stars? It's tough. It's pretty polluted. I mean, the whole Boston area is pretty bad, but I bring out my telescope every semester to my class, and we observe near one of the dorms where there's lots of lights, but we can see like the moons of Jupiter and the rings of Saturn, and like we can see all sorts of stuff. So yes, you can see stars. Tufts is also it's pretty accessible if you have a friend with a car or get a zip car, or, borrow a car or something, you can get out to like the middle of nowhere very, very quickly, and see lots of stars. So how difficult students, School of Engineering? Oh, Emma's taking that one. Good. How does Tufts support, encourage research? I mean, I would say like most faculty really want to have students in their research groups. There's some funding if you're on like work study to work in research groups, but lots of faculty have funding, or you can volunteer. And I would say most faculty, particularly in the STEM fields, which is what I'm familiar with, are very open to having students be involved in their research projects. It's how we all learned, and it's how we learn, and it actually creates a really lovely community. So I would say like whether you're at Tufts or elsewhere and interested in pursuing a career in science, get involved in research. Have I done research on the black hole? I don't I don't understand the ton 618. Is that a specific black hole? If it is, I have not. I don't I mean I don't study. I teach about black holes, but I don't study them. I mean my like focus is on these tiny little stars, and more specifically, like I said, how old they are and actually how they generate magnetic fields, which seems very esoteric, and it is. Oh, well, I'm super biased. You should take my class. The best STEM courses for non-STEM. Can everyone read the questions, Emma? Should I have been repeating all of them?
I don't think they can see them,
Oh,
but
okay. Well, that's my bad. I'm sorry. I'm usually good in class. If someone asks a question, I repeat it. I just figured I didn't want to be like the person reading. Okay, what are the best STEM courses to take for non-STEM oriented students? Okay, I figured that out too late, but oh well. Um, and that's why I said like, of course you should take my class. My class is mostly for I mean, almost everyone who takes it is a non-STEM um major. I guess you can probably read things online about which ones they enjoy. I'm sure there's all sorts of posts, some of which I've read, some of I haven't. Um, I think mine are mostly positive unless you're a student who cheated in my class, which we don't need to talk about. Other things? I mean, concepts of the cosmos is an intro astronomy class that's taught most semesters at Tufts that I know is very popular. And as long as you're willing to do a little bit of math, but not a lot, it's actually very popular as well. But I don't teach that on campus.
Great. Well, thank you so much for your time. Lots of great questions from all of you students as well. Thank you so much for coming out to this event. We have lots more exciting events coming up going into mid-October. So if you enjoyed this class, we have other mock classes and other events happening as well. Check out the rest of the Fall for Tufts events. And Have a great evening, everyone. Thank you so much.